Hello, folks, and welcome to day 2 of Enzyme Kinetics. So here are the learning outcomes for the day. First, compare and contrast the two key assumptions of Michaelis-Menten kinetics, the type of kinetics that we use to study enzymes. We will define some new vocabulary, Km, Vmax, Kcat, and catalytic efficiency. And finally, we will draw appropriate Michaelis-Menten kinetics curves given Km and Vmax, and be able to draw both those traditional curves and line mover Burke plots, which are a new way to visualize the data. Today's Meet a Scientist moment is Kizzy Corbett-Hilaire. She is an assistant professor at Harvard University. She's a Black woman, and she studies the coronavirus. And you may already have heard about her because she led the team that developed the Moderna vaccine, which some of us may have already been vaccinated with. Let's jump into the material, folks, and let's start with understanding why do we need to know this in the first place? Why is enzyme kinetics important to know? And so the big idea for most of us who think about enzyme kinetics is we need to understand how to impact biological processes that are done by enzymes for therapeutic reasons. Think various disease states or illnesses, right? The vast majority of drugs that are available on the market target enzymes. And so we can't understand how those drugs work without knowing how the enzymes work. Furthermore, we can't understand how those drugs are metabolized by our body without knowing enzyme kinetics. And also, of course, personally, I think sometimes it can be fun. On the screen, folks, I'm showing you the reaction scheme for enzyme kinetics in biochemistry. And we can use this same reaction scheme for a variety of enzymes that have very different types of mechanisms. Let's walk our way through it. So we start off with enzyme and substrate. They have not bound to each other yet. Then that enzyme and substrate can bind, and the binding is represented by the rate K1 to form the enzyme substrate complex, where the enzyme has bound to its substrate. The rate K minus 1 is the rate of dissociation or unbinding. Once the enzyme substrate complex has formed, you have the rate K2, which represents the chemical reaction being performed to turn substrate into product. And you can hear in this reaction scheme, folks, we've kind of skipped a step where we're showing you the enzyme substrate complex turning into the enzyme product complex. Because you see the enzyme substrate complex just becomes enzyme plus product at the end. There are a number of things that biochemists do in order to make the math easier to understand so that the kinetics are simplified, okay? One of the things that we do to make the math easier is when we're setting up these reactions in a laboratory setting, we make sure that the concentration of substrate is much, much greater than the concentration of enzyme. What this does is it allows the reaction to be 0th order, which means easy math. You learned about reaction orders way back in Gen Chem. I don't expect you to remember this. I'm only saying this to kind of convince you that we set up the experiments in a way that the data is easier for us to understand. Also, when enough substrate is present, we can basically assume that nearly all of the enzyme is bound to substrate or in the enzyme substrate complex. And this allows for the second step to be rate limiting. Let's jump into a bit more detail here. There are two key assumptions of Michaelis-Menten kinetics that are going to be true regardless of the enzyme and substrate that we study. The first is the assumption of equilibrium. In other words, we are assuming that K1 and K minus 1 are much larger than K2. K1 and K minus 1 are much larger or much faster than K2, and K2 is slow, right? Thinking back to that last slide, remember K2 is the rate limiting step, it must be slow. And when we assume equilibrium, or we're assuming that K1 and K negative 1 are so fast that we've reached a state of equilibrium where the rates have equalized themselves, that then allows us to have this second key assumption, the assumption of steady state. And steady state, I want to emphasize here, is different than equilibrium. In equilibrium, we're talking about rates of reaction. And in steady state, I want you to think that is more of homeostasis, or that the concentrations of things aren't changing. So steady state is more an idea of concentration, or homeostasis is probably fairly comfortable for most of us to think about. And so also assuming steady state, that means the concentration of the enzyme substrate complex is not changing over time. And the mathematical representation of that is on the slide as well. I can also show these two things to you graphically to kind of just further, in more detail, describe these two key assumptions. Let's start with assumption 1, assumption of equilibrium. So we are assuming that the K1 and K minus 1, the rates K1 and K minus 1 have become equal to one another, right? Where does that happen on the graph? So if K1 and K minus 1 are equal to one another, that means that the amount of enzyme substrate complex should stop changing. Where on this graph have we reached that point? Well, it looks like here, folks, we have achieved equilibrium, right? Up until this point in the graph, you see that the concentration of enzyme substrate complex is increasing, and you see the concentration of free enzyme is decreasing. But right at this point where I've indicated, this is where assumption 1 is met. So in this area, starting from here on, we meet assumption 1. Now, where on the graph have we also met assumption 2? Steady state, where the concentration of enzyme and substrate complex isn't changing over time, okay? And so that is represented by this darker box that starts with assumption 1, but then ends later on once we kind of see after this point, right, folks, that the enzyme substrate complex concentration starts to drop off. So this whole range here is showing us where assumption 2 has been met. And when we set up reactions in this way, this allows us, excuse me for a second, this allows us to perform reactions in the lab in a way that becomes easy for us to understand. And we can gather important information from that data. So up next, we'll talk more about Michaelis-Menten kinetics and get into some of that new vocabulary.